Hey guys, so in this tutorial we'll be discussing ensemble methods, okay? And this is actually one of the nicest areas in machine learning and I guess the most important area in machine learning before deep learning. Um, and it gave us classifiers such as the random forest or algorithms rather than classifiers, um, and boosting. So you may have heard of XGBoost. That's a form of boosting. Um, and these two guys here are probably some of the best algorithms out there, and they actually, in my experience at least, they achieve uh, usually better performance than deep learning on a lot of tasks. So probably not image and speech recognition, but if you're just trying to do kind of a standard data analytics task, usually these are my go-tos just to see what a baseline should be. And the other reason that they're really nice is that they're really simple. So sklearn, uh, scikit, scikit-learn in Python. This is about maybe 2 or 3 lines of code to use either of these. So it's a really nice algorithm that's very simple, and it's kind of straight out of the box, whereas in deep learning, I guess, takes more tuning and getting used to new packages. So anytime you have a data task or prediction task, you should go to these two and see what kind of output you get. All right, so these are just two types of ensembles that I'm going to be talking about today, but there's a bunch of them. And basically, I'll start off with random forest, and then I'll talk about boosting in detail. So instead of just kind of explaining what a random forest is, I'm going to start off from the basics um, of the bias variance decomposition, and then I'm going to work my way up into the random forest algorithm and why the random forest algorithm was motivated by the problem of the bias variance decomposition. So bias variance decomposition. Um, and you would have heard of this in the first week, and probably if you've done any kind of statistics or machine learning, you've definitely heard of this. But I think a lot of people don't really kind of grasp this topic or this particular decomposition. So I'm going to try my best today to try to explain it without using too much math. I'm trying to use examples and figures. We'll delve quite deep into this decomposition. So before I do that, I just want to explain what bias is and what variance is. Okay, so remember from a few weeks back, we talked about the bias, and let's say we have some. Uh, so actually, let me just write it here. Assume we want to estimate some population parameter theta, and we have a sample x1 to xn. So this is kind of the standard machine learning task, right? I'm talking about an estimate. I'm talking about a parameter here, which in regression is just the regression vector, or in perceptron it's the weight vector. In any model, you have a set of parameters that you're trying to estimate, and what you have access to is the data. So this is kind of a simplified example, a simplified setup of what we do in the what we've been doing for the last few weeks. So just a concrete example, imagine that you have x1 to xn from a normal distribution, right? And your theta is the population mean, mu. Now you don't have access to the mean, but you have access to the samples. So you might estimate theta hat. So theta hat is the estimate of theta. You might estimate this guy by looking at the sample average. But you can also look at so let's say another estimator, you can look at the sample median, okay? So there's a bunch of ways to do this. There's an infinite number of estimators. that you can use. And the bias variance decomposition tells us that you can decompose the error of each of these estimators into a bias portion and a variance portion. So I'm going to get into the details of that in a minute, but this is kind of the setup that you should think of. We're trying to estimate a parameter. We have an estimator based on a data set, a sample, and so in this case, the bias is the expectation of the estimator minus the truth, okay? And the variance is just the variance of the estimator. So variance of the estimator. So bias, I should stop changing colors so dramatically. So bias tells us, kind of how far from the truth are we? So this is just kind of a hand-wavy definition, but it's it's looking at the expected value of the estimator, and it's looking at the distance from the truth. Okay, so the expectation minus the truth. So this quantity here will tell us kind of how far we are from the truth, and the variance tells us how noisy our estimator is. Okay, and so I just need to be really clear what the expectation and variance are being, or how we're actually computing these expectations and variances. So it's actually, this is kind of a subtle point. When I talk about the expectation, or let's talk about the variance. When I talk about the variance, okay, so it's the variance over many data sets, right? So imagine that we have our first sample, x1 to xn, let's call this d1, and then I build my estimator, theta hat 1, and then I take another sample, and I'll call this, let me call this x11, x1n. And then I have another sample, x21 to x2n, and I build another estimator, theta hat 2. And I just do this forever, right? So I get infinite number of estimators. The variance is looking at how much do these estimators change, or how variable are these estimators across different data sets. Okay, so the expectation and the variance are actually taken over the data sets. Like each time I get a different estimator, right? Each sample will, let's say I'm using the sample average, right? Each sample is going to give me a different sample average, x bar 1, x bar 2. But if they're all coming from the same population, so I can measure the expected value of these, so I can average over these minus the truth and see how close I am. And I can also compute the variance of those estimators and see how variable it is. Okay, so this is probably going to sound still quite vague. We're going to really dig deep into this concept, but I just wanted to introduce the bias and variance for the simple case where we're looking at this simple setup. So there's a picture to keep in mind that's really useful. And you would have seen this in the lecture notes, so let me try to draw it neatly. Okay, so it's a grid. It's a 2x2 grid, and in each grid we have a target. So let me just use these tools to make it really neat. Okay, so that's a target, kind of, and let me just copy them into each of the four. Okay, and on this side we're going to have bias and variance. Okay, and here we're going to have low and high, and here we're going to have low and high. So in this quadrant, we have low bias and low variance. In this quadrant, we have low bias but high variance. And basically, you're going to think of this as so forgive my drawing, but just imagine that this is theta hat, and he's holding the gun, or he or she is holding the gun, and they're taking shots. They're shooting a bullet, or a bunch of bullets rather, at these targets. Okay, so when it's low bias, right, it means that bias, just from my definition here, looks at how far from the truth we are, right? So if it's low bias, it should be close to the truth, and I'm assuming the truth is the center point here, okay? So if it's low bias, it's going to be close to the center. Now, if it's low variance, it's going to be not too spread out. So variance measures the how noisy our estimator is, or the spread. Okay, so you can think of these individual bullets as different data sets: data 1, data 2, data 3. So I get data 1, I build my estimator based on this, on whatever estimated this is. So this could be like x bar 1, x bar 2, x bar 3, for example. And the truth in the middle here is mu, the population parameter. Okay, so the bullets are, each bullet is a different data set. Each bullet is an estimator built on a different data set, but they're all based on the same estimator. And the truth is the true parameter that you're trying to estimate. So where do these bullets land? Well, low bias, low variance means we're going to basically, on this picture, we're going to land really close to the truth, and we're not going to be very spread out. Okay, so it's really tight around the center, around the truth. And of course, there's still going to be noise, right? Because there's just randomness inherent in any statistical task. But the point is that the spread is really, really low, and they're centered on the right point in the space. So this is kind of the best case scenario, right? It's really great to have low bias and low variance. That is the ideal case. Now, if I have low bias but high variance, well, low bias means I'm still going to be centered around the truth, but I'm going to have a very high spread. So I kind of know where I'm shooting, but I'm kind of like, I'm not very precise in my shots. So you can see that it's still, on average, it's like if you average these guys, it's still going to be the right point in the middle, but the spread is kind of imprecise. Okay. Now, if I have a high bias, but low variance, what does that mean? Well, high bias means I'm actually not aiming at the right spot. I'm aiming at some other spot here, maybe, for example. But the fact that I have low variance means I kind of aim at that wrong spot with high accuracy. Right? Sorry, let me draw that again. I aim at the wrong spot, but with kind of with low variance around that point. And finally, if I have high bias and high variance, then this is kind of terrible. This is just, I'm focusing on the wrong spot, and I'm not being very precise. So you can think of this as the worst case scenario. Okay, and I want you to keep this in mind when we look at the examples that I'm going to go through. But it turns out that it's not really simple. It's low is the best case scenario, but it's not very simple to actually get an estimator that's really low. Low in both, because there's actually a trade-off between the bias and variance, meaning that when I decrease bias, what ends up happening is variance increases, and when I decrease variance, bias increases. So there's actually it's actually a trade-off, and you need to kind of pick the estimator that kind of is the sweet spot between bias and variance. So the bias variance decomposition. We're going to focus on this scenario. We have so we have a true function. The truth is the function f of x. So this is the true function, whatever it is we're trying to estimate. So now I'm not really talking about estimators and parameters. I'm talking about a whole function. So you can think of bias variance decomposition as holding anytime you're trying to estimate something. It could be a parameter, it could be a function, whatever. So here I'm just going to assume that we're going to talk about functions because I want to look at the bias variance decomposition most widely seen in machine learning. And we have our estimate, f hat of x. And sometimes you'll see this written as f hat of x d, because this f hat is built on the data set d. So d is equal to a set of points xi, yi, for I equals 1 to n. Okay, so this notation means that this particular estimator was built from this particular data set. Okay, and for different data sets, obviously we're going to get different function estimates. Okay, and we want to look at the expected mean squared error on a test point x0. So basically, I just want to know what is my expected error. So mean squared error is just squared error, right? So x minus y squared, and we sum over all the points. You know, we're not looking at x and y here, but you guys know what mean squared error is. It's just the average of the sum of squares. And I want to look at the error at some point xo, which is a test point, so I haven't seen it before. And it turns out that we have this decomposition, and I'm actually using the notation used in the Wikipedia page because I actually think that's kind of the clearest, one of the clearest definitions. So let's look at it. Okay, so this is this term here is the expected mean squared error at x0, right? Sorry, this should be, I should have f of x0, right? So this is the truth. F of x0 is the truth at x0, right, for the true function. F hat of x0 is my estimate based on my estimate f hat, and it's built on dataset D. And so I'm looking at the expectation of the squared difference of those two. That's the squared error, okay? And it turns out that we have this decomposition, the bias of the estimator squared plus the variance of the estimator. Okay, and this is the bias and variance at the point x0. Okay, and usually, well, not usually. I mean, we'll also have a sigma squared term here, which I'll explain in a bit. And just let me write out what is the bias. It's the expectation. So expectation of f hat xo d minus the truth, the whole thing squared, plus the variance. So when I write this d, by the way, I'm going to explain that in a minute, but I mean that we're taking the expectation over data sets. So it's like the concept I talked about before. And the variance of the estimator plus sigma squared. Okay, so let me just quickly explain what is sigma squared. This is the irreducible error. Okay, so in every statistical task, we're just going to have some randomness, right? Randomness due to not being able to measure something, or just randomness due to chance, or you know, some kind of randomness that we are not able to model. So every time I'm looking at the expected error, there's always going to be two things that I can do something about, and there's also going to be this piece that I just can't do anything about. It's called the irreducible error. Okay, so I'm not going to say much about that, but you can Google this if you're interested. But yeah, we always have that. Now, this is the bias term, or the bias squared term, and this is the variance term. Okay, and so what this tells me is that if I want to reduce test mean squared error, right, I should reduce bias and reduce variance, right? I want to be able to pick estimator f hat such that I have low bias and low variance. And the problem is, there's a trade-off between these two, as we'll see in a minute. So as you reduce variance, you're actually going to increase bias and vice versa. So what that means is when we want to reduce MSE or test error, we're actually going to have to pick an estimator that trades off the two, in the sense that we can afford a bit of bias to reduce variance somewhat, and vice versa. Okay, so I want to kind of explain, I really want to talk about this expectation and this variance. And what I really want to focus on is what does this subscript mean? Okay, this is really important. So let me draw this picture. The way I like to think about it is I have some black box, okay, data generator. Okay, so what this kind of means is that what do we do in machine learning usually, right? Machine learning pipeline is I get a data set, I build a model, and then I kind of evaluate model somehow using using cross-validation or whatever. And then the fourth step is to use model in the wild. Okay, this is kind of the basic process. What I'm focusing here is this first step, right? What does it mean to get a data set? Well, this data set is a set of XY pairs that were kind of generated by some relationship, right? There's some true relationship between X and Y variables that I'm never going to see. But the point is I want to try to model the truth based on the sample. Now you can think of the sample that we get as being this D1, which is X1, Y1, up to Xn, Yn. Okay, so your whole machine learning pipeline is that you get this D1, you build an estimator or a function f hat 1, and then you go out and use that model. But what I want you to picture is, imagine that you had access to this black box and you could sample another data set, D2, and get another estimator, f hat 2, and D3, and get a third estimator, f hat 3. So by the way, what I mean here is that this is the same thing. So let's say I did a neural network with 5 layers, 5 hidden layers, and the width was the same. I would build a neural network on the first data set, then I would build a neural network on the second data set, third data set, using the same architecture, but different data. So every estimator is going to be different in the sense that they're seeing different data points, but they're going to be the same in the sense that it's the same model, same number of layers, same architecture, or whatever. And I'm going to do this, obviously this is a theoretical construction, but I'm going to do this an infinite number of times. And I'm going to get an infinite number of vectors. And when I look at the expectation over D of f hat, what I mean is that I want to look at the value across these infinite number of estimators and take the expected value. When I look at the variance, I want to look at the infinite number of estimators and take the variance of those. Okay. Now, obviously, this is not always going to be infinite. If I have a task, some weird task where there is only like a finite number of data that could be generated, then I can actually compute this explicitly. But just in general, there's going to be an infinite number of data points. An infinite number of ways to sample a data set. Okay, so this expectation, this variance is taken over different data sets. All right, and I really want to draw this home, so I built this little example notebook. So I actually think this stuff is really important, and it's kind of skimmed over a lot because it's kind of heavy on the math. But it's actually I was trying to explain it here with just code and just figures. Okay, so what I'm doing here is I have a true function which I just picked randomly. It's just this cubic function 0.001 x cubed. There's no particular reason I picked that function. Now my my function here, right, f sampler is a way of sampling from this function. So, you know, just in general, if you're simulating a data set, this is kind of useful if you're trying to, you know, test a model or test your own algorithm or whatever. You might pick a true function, call it f, and then you might get a data set. You might generate a data set D1 by looking at a grid of points. Okay, so you pick the x values, and then you compute the f at that x value. So to get your y values, okay, xn. So you compute your corresponding y value at the point, but then you add a little bit of noise. And so obviously you don't want to give it just exactly samples from the function. You want to give it a bit of noise and see what it can do. This noise can be anything, but usually you'll see it being normal, 0, sigma squared, so some noise, but it doesn't have to be normal, and you get to pick sigma squared. So what I'm doing here is I'm generating 100 points. I'm taking my sigma to be just the default value 0.1. And you can see here my x vals, I've just sampled uniformly on the grid from 1 to 10. My y values are the function evaluated at the values plus some sigma times normal random variables. Okay, so sigma times normal is the same as normal 0 sigma squared, right? And then I build my data set and I return my data set. So all this function is doing is sampling 100 points, 100 noisy points from my true function. So let's see what that looks like. Okay, so here in red I have my samples. The true function is in blue, and I have my data set. And you know, as I said, you can do this an infinite number of times, right? You could simulate an infinite number of data sets because every time you're just adding a little bit of random noise, the random noise is going to be different every time, and so you get a different data set every time. So what I do that here. I do this 9 times. Oops, it should work. Okay, here I do it 9 times. And so what I'm trying to explain here is basically this picture. The black box data generator is giving us different data sets. And so you can see here the same true function is the blue function, right? But every time I'm getting a different data set, right? So I have 9 different data sets. And now what I want to do is build a model, build the same model on each of the data sets. And I'm going to get a different model each time because you know, the model is based on the actual data. So I'm going to start off with a really simple model, linear regression or simple linear regression, where I just have a single predictor. So the equation is going to be y hat is equal to a plus b x. The only thing that differs is a and b, right? I'm going to get a hat b hat here that's different to the a hat b hat here, etc., etc. Okay, so let's see what that looks like. Okay, so here's what it looks like. So same data set as above, but now I build my linear regression, the green line. So in green I have my f hat, blue I have my truth, red I have my samples. And you can see that across the different data sets, I'm getting just what you'd expect, a straight line, not very interesting. But the point I want to make here is that we're getting slightly different fits on each of the data sets, but they're not too different, right? They're not too different. So let's look at a point on the x-axis, the 0.5, and I just want to see how how is the estimator doing? How is the linear regression doing at this particular point of 5? Okay, so here I'm plotting all those 9 models that we got. I'm plotting it. I'm plotting the true function, and I'm plotting a line at the value 5, and I'm going to compute the bias squared and the variance. So what do I mean by bias here? Okay, well, I took the mean of the predictions of the 9 models. So the 9 models, right, you can see them in green, they all have a prediction at the value 5, right? Sorry, I've zoomed in way too much. So they all have a prediction at the value 5, and the average prediction is somewhere in the middle, right, somewhere maybe there. And the bias squared is the distance of that point to the truth, right? So the truth is on the blue curve, and squaring it gives me this number here. Variance is looking at the estimates and just computing the variance, the usual way you compute sample variance, right? Now you can see the variance is going to be quite small because linear regression, they're all giving me kind of these really, these straight lines, they're all very close to each other. It's not too wild from different data set to different data set. So the variance is quite small, the bias is quite high. So one way to think about bias and variance, or a good way to think about bias and variance is that, so let me write it here. So a high bias model is has strong assumptions, right? Another way to think about strong assumptions is that the shape of the fit is predetermined, regardless of the data. Okay, so you can see that hopefully from here, that I got different data sets, but the shape is just a straight line, right? The best I can do with a straight line is, draw a straight line. So the shape of the fit is already predetermined before I see the data set. The line changes slightly, but it's not enough to, it's kind of not changing with the data, so it's not flexible. So a high bias model usually has strong assumptions, or does have strong assumptions. You can think of that as just having the shape decided already before seeing the data. And you can see that high bias models are going to have really low variance, because if you're always picking the same shape, the lack of flexibility is going to give you kind of the same fit every time, so the variance is quite low. So what is a high variance model? Well, let's kind of look at let's look at a high variance model and then define it, or kind of discuss what it actually means to be a high variance model. So here the bias is kind of very clear, and you can think of also the bias as being kind of the inability of a function to estimate the truth, right? The truth here is a curve, and we only have a straight line, so it's quite high bias to assume a straight line every time and not adapt to the actual sample. All right, so what I do here is, we can build a more advanced model by looking at polynomial features, right? So what I mean by that, I mean that I can just write it here. Now we're going to have a plus b x plus c x squared. Okay, so this is kind of still linear regression, right? But it's kind of, we're actually fitting a polynomial. So this, taking the x squared term, allows us to fit curves. And so this is just a feature transformation, but it actually increases the complexity of the model, and it gives us more flexible models. Okay, so let's see what that looks like here. So I'm doing the same data sets, but now I'm fitting the features x and x squared. And you can see the fits are in green. Now they're capturing some of the curvature in the model. Okay. And if I do the same thing I did before, now you can see that the bias has actually gone to 0, because it's actually capturing the curvature of the truth quite well. The variance has increased, right? The variance has increased. And so why is the variance increased? Well, if you think about it, we have like more flexibility in our model, right? We can pick models that have these two features. So we can actually fit in the previous example, we were just fitting straight lines. Now we're fitting quadratic functions, right? Quadratic functions are more flexible. There's more quadratic functions to kind of choose from in a way. And so what happens is that the quadratic function is able to kind of get the curvature. But the problem is there's noise in the data, right? There's noise in the sample. So what happens is that as you get more complexity in your model, it can try to fit the noise in the data. Okay, so in this particular case, it's not too bad, right? It's not too bad. The variance is still quite low. The bias has gone down to 0. So you can see that the mean squared error that we're going to get from this particular model is actually lower than the mean squared error from the linear regression model. And so that tells us that this is a better model than before. But let's see what happens when I add more polynomial features. So in this case, I add, let me just write it here for clarity. I add a plus b x plus c x squared plus d x cubed. I think I do to the power of 6. Yep. Plus. Okay, so this is my regression. So by the way, this is still linear regression. It's just that I'm adding polynomial features. So I'm able now to, build models that are, so this is going to be a polynomial of degree 6. Okay, so it's going to be a model that can be quite curvy, okay, quite complicated. So again, I mean, this code is not the nicest code, by the way, but all I'm doing is kind of adding these features and then taking a linear regression model and fitting it on those features and predicting what would happen on the grid. Okay, so let's see what we get. Okay, and so you can see here, so by the way, this is exactly the same 9 data sets, right? I haven't changed the data sets, it's the same function. But you can see that the green functions now are really, really flexible, right? They're actually almost interpolating, in many cases, the entire data set, right? So like look at this, for example. We're going to get we're going to get really low error there. And so what I've done here is increase the complexity of the model dramatically, right? I have features x to the power of 6. So you can expect that the bias is going to go to 0, right? Why? Because it's going to be able to reach the truth, right? The distance from the truth is going to be quite low because it's so flexible, right? Flexibility means we can model more and more complicated functions. So the bias should go to 0. But look how different the green functions are in different data sets, right? They're extremely different. And that means that we're going to have really high variance for this particular model. So high variance model is, one way to think about it is how much error we get due to fitting randomness. Right, so you can see here that they're so complex that they actually end up overfitting, right? Overfitting the data and missing out on the blue function almost completely in some cases. So we're getting these really wild functions, whereas our truth is much simpler. So high variance means that on every data set, the model ends up trying to fit the data too well, right? Overfitting the data. And for the same kind of experiment, we look at the bias squared at this particular point, x0 equals 5, and the variance. So you can see the variance is increased. The bias is still 0, as you would expect, because it's such a complicated model. Yeah, so the idea is that hopefully you can see the idea. As I increase the complexity, the bias decreases, the variance increases, and the variance is not. You can't look at the variance in just a single data set. You have to look at it across different data sets. Okay, and that's what I'm trying to explain in this kind of picture here. This is really important to get your head around when we talk about the bias variance decomposition. All right, let's continue on with the example here. All right, so that's hopefully quite clear. So I've got some explanation here. The high variance comes from the fact that different data sets give us very different models. So another thing this shows is the trade-off, right? So low bias models have high variance. So this particular model is an example of that. But high bias models like linear regression have low variance. And we need both of those to be low to get mean squared error to be low. So a good trade-off in this case was this middle model, right? The quadratic model, right? So what you would do in practice is maybe, try to pick a model that's complex enough to fit the truth, but not too complex that it starts to make up its own story, right? This one is making up its own story. It's got a very dramatic story about how the data was generated, right? These are very dramatic functions in a way. All right, so what I do next in this notebook is, well, I've only looked at 9 data sets, so let's look at more data sets. I'm going to do, I think, 80 data sets here, and here I changed the function to be something a little bit more exciting, so it looks like this. But same exact process of picking a true function, then sampling from the true function. And now I want to generate 80 data sets, and for each data set, I'm going to have 25 points. And what I'm going to do is actually build a linear regression model with polynomial features starting off at 1 and going all the way up to 9. So I'm going to have to the power of 1, to the power of 2, to the power of 3. And I want to basically see what happens as I increase the complexity. So let's plot it out. Okay. Now, let me make the picture a bit clearer. So, okay, so what's happening here is that I've got my true function in red. That's the bright red one. And then I've got my so I've written here expectation of f hat. This is not really truly the expectation of f hat because the expectation is an infinite number of data sets, and here I'm only looking at 80 data sets. But I'm just kind of just for visual purposes, I'm going to call it an expectation of f hat. And I'm looking at the entire range. So the blue points, the blue lines are the fitted models for the 80 data sets. So every one of these guys, so in this example, every blue line is a linear regression with degree 1 feature set built on 80 data sets. The red line is the truth. That's the true model that generated the data. And then the orange line is the mean value across the points on the range. So it's just the averaging of the blue models gives us this red point. And if I look at bias, right, I should look at the distance from the truth to the expected value and square it each time, right? So the distance is just these values here. The variance is going to be the variance across these models, the blue lines, okay? Now I increase the complexity, okay, to a polynomial of degree 2, and I get the same picture here. The blue lines are now the quadratics that we fit and on the 80 different data sets. The orange line is the averaged value of those data sets. And similarly for degree 3, I'm getting, so you should see hopefully that the orange lines, the averages are getting more and more complicated, right? They're getting able to fit more and more complexity. When I take it up to, say, polynomial degree 5, degree 6, I'm starting to get better and better looking average functions. And so what this is saying is that the complexity needed for this particular red function is higher, right? And one thing I should note here is that you should really just ignore the endpoints. You see how the performance gets really dramatic, really quick here at the endpoints. You should ignore that for this particular example and just focus on points closer to the middle. The reason I want you to ignore it is because this is just an artifact of the actual linear regression model, it's not really got anything to do with bias variance. So this is just something bad about the actual model I'm using. But I don't want to get into that. Just look at the inside 90%. So maybe from the 0.1 to the 0.9, look at the performance of these models. And so you can see that as I increase the complexity to degree 9, I'm getting almost perfect, like look at this almost perfect matching of the truth, right? So the bias is going to be 0, right? Almost 0 for this polynomial of degree 9. But look how crazy the fits are, right? There's going to be quite a bit of variance there. All right, so actually it's not too bad in this case. Like if I did, maybe I should have done polynomial degree 20 just to show really high variance models. But hopefully you get the picture that the variance is kind of definitely increasing as I go from top to bottom, right? The variance here is really kind of small, and as I increase, I'm getting wilder and wilder models. Okay, whereas bias is really high here, like the bias is really bad, and as I increase the complexity, the bias is getting smaller because the orange function is getting closer to the truth. Okay. Now, I think that's kind of it for the bias variance decomposition. What I did here is just to actually plot for the 9 sets of models. Sorry, we have 80 models for each degree, right, of features. So for the linear models, I look at the squared bias. So you can see that the bias, so obviously you're not going to get a picture that's perfect in these cases because there is randomness, but you should see that the lower degree models, right, so blue, orange, green, are generally at the top of the bias curves, right? They're getting really high bias generally. And if you look at the bottom here, it's kind of hard to see, but the pink and this kind of olive color and gray color are really low at the bottom. These are the high degree models. Okay. In contrast, when you look at the variance, so this is the plot. So by the way, this is the plot of the variance against the degree. Sorry, this shouldn't be degree. This should be against the x values. My mistake. So this is the x values from 1 to 10, and each of the curves is the degree. Now here, you should see that the high variance models are the ones with the really high degree, right? So see this olive curve is the variance of the really complex model at the end. And look at the lowest variance is that blue curve, which is the degree 1, just the straight line model. And so for you, like doing modeling, right, the model that you should pick should have a low value for this plus this, right? You want to, the mean squared error is the squared bias plus the variance. And so, the mean squared error is going to be, there's going to be a trade-off between these two. So you're probably going to pick a complexity somewhere on the scale between degree 1 and degree 9. Okay, and so, we have our squared bias, we have our variance. So what I'm going to do now is just add them together. So the mean squared error, right, for a test point x0 is the sum of the bias squared plus the variance plus sigma squared. I'm going to ignore sigma squared here. It doesn't really tell us much because we have no control over it. But I'm going to basically try to plot this for all values of x0 for our example. So what I do here is just add them together. And let's see if we can, this is just an example that I came up with. So, you're always not going to get 100% perfect, visualization of what you expect in theory. Okay, but I'm going to try to see here. So the degree 9 polynomial, you can see that it's the olive one. So the variance just, the mean squared error is really, really high, right? At the endpoints, like I didn't even come into our plot. And that's, again, an artifact of the model, not really anything to do with the bias variance decomposition. And so you can see that it achieves pretty low test error across the board. You can see the blue model, which is the simplest model, is actually achieving pretty bad test MSE, okay, across the board. And same thing with degree 2, degree 3, so the orange and the green, and the red is degree 4. So you can see that it's favoring models that are pretty low complexity. Now, if I take the average over these values, you can figure out maybe what's the lowest average test MSE. I don't want to do that because this is not a very good model, especially on the ends, but you can kind of get an idea of how you would pick the right complexity. Okay, and this is kind of the idea behind cross-validation. In cross-validation, you're trying to estimate this particular value. Obviously, you don't have access to the truth, whereas here I'm cheating. I actually do have access to the truth. So you can think of cross-validation as trying to approximate this particular process that we're doing here. Okay. All right. So I'll make this available for everybody, but hopefully this is kind of. I mean, this is a really important idea, and it's usually kind of skipped over because of this D subscript, which kind of looks scary because we're, what does it mean to average over different data sets? But it just means that we want a model that's kind of robust across different data sets, because there's no reason, like going back to this example, you get a data set, there's no reason that data set captures everything about this black box perfectly, right? So there could be an infinite number of data sets, each with slightly different variations and giving you very different models. So you don't want a model that's like very, very different every time. And you don't want a model that's also very high bias, strong assumptions each time. So you want something flexible enough, but not too flexible for your particular task if you want to reduce test MSE, or in other words, if you want your model to be able to generalize to new data. Okay, so that was kind of the long way of introducing random forests. One particular example of a okay, so I'm gonna kind of introduce ensembles. So back to ensembles, but I'm gonna motivate it. So I've already motivated why. I've already motivated the bias variance decomposition, but now I want to talk about what an ensemble is and how this how do ensembles approach the bias variance decomposition problem, or how do they? I mean, they were kind of motivated by the idea that bias and variance are traded off. So let's kind of go back to a simple example of decision trees. Okay, so what is a decision tree? So let me just do a two-dimensional decision tree with two features. So what is a decision tree? It looks at the value of x1. It probably has a split, let's say x1 less than 50, x1 greater than 50. And let's say in this case, it classifies as -1. In this case, it looks at x2 and breaks x2 into, let's say, x2 greater than 100, x2 greater than or equal to, so x2 less than 100, and let's say it classifies like this. So this is an example of a decision tree, and so what does this look like in terms of the decision space or the decision boundary that it's coming up with? Well, if we look at x1, we're splitting that at 50, and if we look at x2, we're splitting it at 100. Okay, and we're classifying everything in here as a positive class, everything here as a negative class, everything here is a negative class based on this tree that I drew here. So what that means is that the decision surface that we're getting is looks like this. Let me pick a different color. So red means positive, and blue means negative. Okay, so this is the decision surface we're getting. We're saying that any point that falls into this rectangle is going to be a positive. Everything outside is a negative. Now I can make my decision tree more complex. So let me copy this one down here, and let me make it more complex by adding an extra split. Okay, so let's say if you came down here, then you would test x1 again, and you would check if it's less than 25 and greater than or equal to 25. Okay, and let's say we have this. Now, what does this mean for our decision surface? Well, let's look at the first split, splitting at 50. The second split splits at 100. But this third split looks at if x2 is less than 100, then we look at x1 being bigger than or less than 25, so we split again at 25 at this point here. Okay, and we're still going to classify +1, -1 here, but inside of this split, we're going to classify -1, +1 like this. So in terms of the decision boundary that we're learning, or that this tree has learned, we're actually looking at this. We're actually classifying this area plus this area. So all of this is going to be positive now, and everything else is going to be negative. So what the point I'm trying to make is decision trees are an example of a really low bias model, because they actually don't have a particular predetermined shape, right? They just kind of they're flexible enough to fit anything, really, and you know, that's why we get these really crazy looking decision surfaces. So decision trees are low bias. Okay, they don't have a strong assumption about anything. They're just kind of these flexible if-else statements. And what about the variance? Well, you can see that they're going to have really high variance because they can fit basically any noise in the data, right? They can fit any decision surface by just, if you keep splitting and splitting and splitting, you'll get these really weird surfaces. So you might get a surface that looks like, you know, like if I just add this additional plus, and then I add this additional plus, and maybe something here, and maybe something here, right? So the decision tree is capable of modeling this decision surface, right? But if I get a different data set, the chances are it's going to actually make a mistake on those points. And so every data set is going to give me very, very different decision trees. Okay, so hopefully you can kind of just see this intuitively. You know, as I see, you know, and by the way, when I draw this, I mean that, you know, let's say the true decision surface. Sorry, let me make this. Let's say this is the truth. The truth is that this is the truth. Okay, so this is the true model, and each time I sample from this model, I have some noise. So I might get pluses here. Okay, and then a different sample. Sorry, and there, I'll draw the negatives in a minute. And say, okay, and the negatives are like this. So these are two possible models from this. So this is all negative. These are two very possible samples that you would get from this data set. And the decision tree that I'm going to get from here is going to be really, really different to the decision tree I get from here, right? So that's why we have really high variance and really low bias, because there's a very high flexibility, and so we get low bias, but the high flexibility we pay for in terms of high variance. Okay, so how do we use ensembles to kind of fix this problem or try to remedy the situation? Well, one way to do that is to look at this concept of bagging. Okay, and this is short for Bootstrap aggregation. And let me explain the idea and then talk about why it makes sense. So we have a single data set, D1, right? That's all we have access to. We don't have the black box, right? So we can't. Sorry, we can't actually build multiple data sets. But we can try to replicate this process. So we have one data set, we look at samples, and we're calling them B1, B2, B3, and let's say Bn. And let me just explain what Bi is. This is a sample from D1 with replacement, M points where M is less than N. So D1 is the set of points x1, y1, xn, yn. So we construct B1 by just sampling M points out of M with replacement. So that means that we can actually get copies of the same point in our data set. This is something we can do because we're just using the data set itself to kind of replicate that black box that I explained earlier. And then from the B1, I'm going to build my first tree, H1. So HI is a tree, a decision tree built on the data in B1. Okay, BI, sorry. So every Bootstrap sample I'm going to build a decision tree on. Okay, and then my ensemble is my bagging classifier. Because the idea behind Ensemble is, how do I combine the prediction of a lot of models into one? Okay, and this is a particular example where I have n decision trees, and I have a bagging classifier. The bagging classifier is going to be defined as C of x, which is equal to +1 or -1 if 1 over n Okay, so my bagging classifier is going to be classifying the point. This is a new point. It's going to be classifying it as a positive class if what I'm going to do is compute the classification of every single tree, right? It's going to spit out +1 or -1, right? Each one is a decision tree of its own. It spits out a class, but I'm going to average over all the predictions, and I'm going to see if those predictions, if the average is positive, then that means that most of them agree that this point is a positive point, and otherwise it's going to be a negative point. Okay, if this is negative. Okay, and the idea is that I average over many independent. Well, before I talk about independence, I average over many trees. Okay, and why does this idea work? Or why does this classifier give me anything good? Well, if you think about the bias variance decomposition, okay, let's look at the bias of the, well, sorry, let me open a new slide here. So, so why does model averaging work? So this is called model averaging because we're averaging over a bunch of models work. Sorry, we're averaging over a bunch of models. So why does this work? Well, let's think of an idea. Let's think of the case where we have a bunch of random variables which are independent, and they have a mean, mu, and a variance sigma squared. Okay, so what this means is that the expectation of yi is equal to mu, and the variance of yi is equal to sigma squared for all of them, and they're independent. If I look at the sample average, well, sorry, not the sample average, if I look at the average, and I look at the expectation of the average, okay, Well, expectation is linear, so I can take the expectation inside. Okay, what is the expectation of yi? Where it's just mu. So I get 1 over n times the sum from 1 to n of mu. And this is just a sum of mu n times, so I get just mu. Okay, in other words, that the expectation of the average is just equal to the same expectation as each of the individual components, right? So the expectation of the average is the same as the expectation of the individual components. What about the variance? Well, the variance, first off, this is a constant, so we can take it outside, but we have to square it. So 1 over n squared times the variance of the sum. Okay, and what is the variance of the sum? Well, if these are independent, right, the variance of the sum, the correlations are all 0, so the variance of the sum is equal to the sum of the variances. And the variance of yi is sigma squared, right? So this is going to be 1 over n squared times the sum of sigma squared. And the sum of sigma squared, well, sigma squared doesn't have an I in it, so this is just the sum of sigma squared n times, so we get n sigma squared over n squared, which is just sigma squared over n. What is sigma squared over n? Well, it's going to be smaller than sigma squared, right? Because I'm dividing by a positive number, so sigma squared over n is less than sigma squared. So the average has the same mean and lower variance than the individual models or the individual values. So in other words, the average of the decision, or the average of n models with bias b, right? So bias is going to be the expectation of f hat minus the truth, right? So if the expectation of f is just, sorry, if the bias of f hat is just equal to some number b, then the bias of the average is also b, right? Because the expectation of f hat is going to be some number, but the expectation of the average of a bunch of f hats is also going to be that same number, right? That's what we just showed here. So the average of n models of bias b is still b, so it doesn't change, but so sorry, I should say here independent models, but the variance is lower. Okay, so I know there's quite a bit going on here, but what I'm saying is if you take the average of independent variables, they're going to have the same mean but a lower variance. And so that's the idea. If you have a bunch of models with the same bias, you can actually achieve the same bias but a lower variance by just averaging, right? So this idea here, this idea here is that this classifier is going to have the same bias as the bias exhibited by the individual models, right? But the variance is going to be much lower than the variance of the individual components. So averaging over many trees or bagging trees, the idea is that you reduce the variance without affecting the bias. So you actually get a much better model, and this is all stemming from the bias variance decomposition, right? Because we know that we can reduce test error only one of two ways: reduce bias or reduce variance. So that is basically the idea behind bagging, which is an example of ensembles. And the one thing I didn't really talk about is the really important assumption here is that we have independence, right? Because if you don't have independence, then you're going to have some correlation term here in the variance calculation, and you can actually get increased variance, which is pretty bad. So we need to make sure that the individual trees are independent of each other somehow. And we can basically do that in two ways. So notice here that when I sampled, I'm sampling randomly. So that kind of induces some independence. So randomization kind of induces independence. So this is crucial to making this thing work. And there's two types of randomization. Randomize kind of across the samples, right? Which means that we pick from the original data set, we pick small subsets of data randomly, so that the data that H1 is trained on is really different to the data that H3 is trained on, et cetera, et cetera. And the idea that we do with replacement gives us more data to work with, and so somehow you get even more independence. And the other way that is common is randomize across features. And this idea here is a little bit more advanced, but it is basically the difference between bagging trees and random forest. Okay, and this algorithm is pretty amazing in terms of performance and how simple it is, but basically all it does is it takes these two things. It doesn't just randomize across samples, it randomizes across features, which means that, you know, in our data set, x1 could be a vector, right, of p features. But for the Bootstrap sample, we're going to actually sample x1 tilde. Let's call this x1 b1. We're actually going to sample not only randomly from the data set, but we're also going to randomly sample across the features. So say I take x11, x13, and say x16 and x1p. So instead of building a model on the original features, I build a model on just 4 features. And the reason this works so well, even though it's such a simple idea, is that we go back to this reasoning here. If you can make the correlation here 0, then you're getting pure improvement, right, with every tree that you add, because this number here is going to be getting smaller and smaller. So you really need to ensure that there's 0 correlation. And when you make when you randomize across the features, each model is being trained on less and less similar data, right? So every tree is being trained on really different ideas. Okay, and that is basically the idea of random forests, and I'm not going to code this up. This should be really, really straightforward for you guys to do. You know, as long as you have a decision tree model implementation, you can actually build random forests or bagging trees quite easily. One thing to note here is that the nice thing about Ensemble, well, actually, before I say that, I just want to give some more intuition for why this kind of idea is appealing. So ensembles are, you can think of them as using the wisdom of crowds versus traditional machine learning. So traditional, where you try to build an expert. Okay, so the idea is, like, in traditional machine learning, you kind of try to find all these features. Like, let's say you're trying to predict, you know, trying to predict whether or not someone has cancer. You could collect millions and millions of features, right, and build this really complicated model, like a linear regression model or more advanced. And you would have to have that single model trying to model all the nuances in the loss surface. And that's kind of the traditional view of machine learning and how we should go about things. The idea behind ensembles is that it's really hard to try to get one algorithm to learn everything. Why not try to have many algorithms, many really simple algorithms, try to learn subsets of the problem you're trying to attack, right? So you could have H1 being an expert in one particular feature of the cancer data set, or 5 particular features, instead of a million, right? And so as you average over the decision of the crowd, of the many kind of, not experts, but the simpler models that have kind of specialized, you're able to get better performance than just relying on a single expert who has to know everything. Okay, so that's kind of another intuition for this idea, which is a bit more, or a bit less mathematical and more kind of, maybe easier to kind of remember. All right, so that's basically it for this kind of ensemble. The other thing I wanted to mention was that contrary to, or if you compare this to, maybe I'll just finish off talking about the appeal of ensembles is that, if you think about it, your base classifier, which in that case was decision trees, is really simple and fast to train. And so when I build a random forest, right, I'm basically just having to train n decision trees. And so the complexity of the random forest, like the computational complexity of actually building this thing, scales pretty well, like almost linear, I guess linearly for simple cases, with the cost of training a decision tree, which is pretty low, right? Decision trees are pretty easy to build. Compare this with a neural network, which we know the complexity of is not, the complexity is actually increasing in the sample and increasing in the number of layers. And so this can be quite expensive to train to get the same performance as random forest. So the appeal of ensembles is that you don't have to try to build this really complicated thing. You can just have access to a really simple algorithm, but you're combining the algorithm, or you're combining, you're using the algorithm in a smart way by combining many simple models into one. That is basically the appeal, or the nice thing about ensembles. The one bad thing, right, disadvantage, and this is not a disadvantage relative to deep learning. Deep learning has this disadvantage as well, but this is a disadvantage to the simplicity of the base class. So decision trees are really, really simple to understand, to interpret, right? Because if I give you a tree, you know exactly why every decision was made, right? You can just look down the tree, you can say, okay, well, x1 is bigger than 50, so that explains why this decision was made. With random forests, lose any easy interpretability. Right, if I'm averaging over 1,000 trees and each tree is built on a different data set and every tree is built on a different feature set, then I'm going to lose that nice interpretability that I had with decision trees. Okay, so that's basically it for bagging and random forests. That's one kind of ensemble. The next kind of ensemble that I'll talk about is boosting, which is pretty similar to this, except that if you look at this classifier here, what I'm doing here is taking the majority vote. So I have n models, I take the vote from every single model, and then I just take an average. That means that I'm averaging over each model and giving each model the same weight, right? I'm giving each one a weight of equal to 1. The idea behind bagging is that we actually have weights here. So each model gets a different weight, and each model itself is trained in a slightly different way to improve performance on the previous model. So let's dig a little bit deeper into that.